Welcome to this lecture series in linear algebra. In this lecture, we'll learn about self-adjoint operators, and let us recall a few things. So this is a fact that we proved a long time ago. If V is a real vector space and T is an endomorphism on V, then one can find two vectors U and V such that not both of them are zero, and these two funny equations hold. So in particular, the subspace spanned by U and V is T invariant, and this is how we showed that every endomorphism on a real vector space affords a one-dimensional or a two-dimensional invariant subspace. We used the machinery of complexification to do this. Okay, another fact which we saw very recently is that if we have a complex inner product space and an endomorphism on it, then this implies that the converse is trivial, but this is more interesting. Okay, so let's move on with this. Here are two problems for practice. And now let us get started. So fix an inner product space, real or complex, and an endomorphism on it. Then we say that the endomorphism is self-adjoint if it is equal to its own adjoint. Very simple definition. Again, it is not very clear as to why this is useful. I will say something about that. But for now, let us just note one thing, that every self-adjoint operator or endomorphism, same thing. Every self-adjoint operator is normal simply because if T is its own adjoint, clearly then it will commute with its own adjoint. This is a trivial remark. And one thing which I want to say is, suppose we are working with a real vector space and we have an orthonormal basis of it. Then for any endomorphism, we can say that so this is a triviality. To say that T is equal to T star is equivalent to saying that the matrix of T with respect to any basis is the matrix of T star with respect to the same basis. Orthonormality has no purpose for this writing this. But if you use the fact that B is an orthonormal basis, you can equivalently say that this is the transpose of this matrix. So I'm sure you know what is a transpose of a matrix. You just interchange the rows and columns, or you can do a quick Google search. So yeah, for a real vector space, checking self-adjointness is in some sense a simple task. You just make the matrices and check this equation. And this is a useful thing. Symmetric matrices arise everywhere. So such a matrix is called symmetric. The matrix which is equal to its own transpose. So if you know what is above the diagonal and on the diagonal, you know what is happening below the diagonal. And these arise everywhere, like in the theory of Markov chains or spectral graph theory, where you make the adjacency matrix of a graph. It turns out to be symmetric. And also in many areas of physics all the time. And you can use it to study second derivatives of multivariable functions. So symmetric matrices arise at a lot of places, and the theory of self-adjoint operators is therefore very useful, because once we are given a symmetric matrix, suppose we are given, let's say, a 2 cross 2 real symmetric matrix, so it should look like A, B, B, D. Yeah, suppose we are given a matrix like that. So then what we can do is we can construct the linear map from R2 to R2, whose matrix with respect to the standard basis is that, right? There is a unique such linear map. And now, by what we just said, this will turn out to be self-adjoint. And now you can hit it by the theory of self-adjoint operators to conclude things about T and hence about the matrix of T. So it does turn out to be very useful. You can prove everything in the matrix setting also, but those proofs I find quite ugly. In the vector space, endomorphism kind of picture, the proofs are much neater and beautiful. Okay, so this is, I think, enough. Let's move on. So first we will show that every self-adjoint operator has an eigenvalue. So fix an inner product space. And an endomorphism on it. Now if we were a complex vector space, then we are immediately done, because every endomorphism on any finite dimensional complex vector space has an eigenvalue. So then we are done. So we may assume that V is real. Meaning the base field is real. Okay, so now thus we can find two vectors u and v and two scalars lambda and mu such that not both of these are 0. So not both and, more importantly, yeah, so this is what we recalled. And now we just consider this inner product. So what is this? This is of course equal to that simply by using the property of the adjoint. And by using the self-adjointness of T, this is equal to this. Okay, so we forget about the middle term. We will be interested in this equality. So the first term is what? Let me centralize this a little bit. The first term is what? The first term is that, and the last term is that, and therefore since we are working over a real vector space, there is no need to put conjugates or anything. So okay, let me write it that way. Alright, and now these two things cancel out. And what we get is, no, something is wrong. Lambda mu, mu lambda. Something is wrong. Just give me a second. No, I think everything is fine. So what you get is mu norm u square plus norm v square is 0. Why do you get that? This is norm v square and that is norm u square, and do the algebra, you get that. But this is clearly non-zero because not both u and v are 0. So therefore this better be 0. So mu is 0 and therefore tu is lambda u and tv is lambda v. So basically if u is non-zero, then we have u as an eigenvector corresponding to eigenvalue lambda. And if v is non-zero, then we have v as an eigenvector corresponding to eigenvalue lambda. In any case, we have an eigenvalue. So we have proven that every self-adjoint operator has an eigenvalue. Okay, let's move on. So now what we will show is that suppose we have an inner product space and an endomorphism on it, then every eigenvalue of the endomorphism is real. So if we were working with a real vector space, this is a vacuous statement. This is obviously true. But if we are working with a complex inner product space, this is something to be proven. So let's prove this. Here is the proof. So let so we are working with V complex. Suppose this holds, meaning V is an eigenvector corresponding to eigenvalue lambda and V is non-zero. Then what we want to do is show that lambda is real. So then this is equal to, clearly, which is all right. but the first term is equal to that. Using self-adjointness, we get lambda bar norm v square is lambda norm v square, but norm v square is non-zero, and hence lambda is equal to lambda bar, which is same as saying lambda is real. So any eigenvalue of a self-adjoint operator is real no matter which vector space you're working with, real or complex. Okay. Here is another thing, small fact that might be useful later, or maybe not, but anyway. So suppose we have a complex inner product space and an endomorphism on it, then it is self-adjoint if and only if this equation holds. Okay. The converse is, one direction is clear. Let me do the not so clear direction. So, okay. Oops. Okay, so we have this thing is real for all v, which is to say that it is equal to its own complex conjugate for all v, right? Which implies clearly by property of the adjoint, which means by property of inner products, which means I'm skipping one step. Which implies t is equal to t star, because this is 0 by what we recalled in the beginning. That's it. That finishes the proof. It's just one small snippet. Okay. Now maybe this is the last thing. Let's finish this quickly. So if we have an inner product space and we have a self-adjoint endomorphism on it, if this happens for all vectors, then this happens. So this is what we recalled for complex inner product spaces. In general, this is true. You don't even need this hypothesis. But with the hypothesis of self-adjointness, you can even say the same thing for real vector spaces. So we will do the proof when v is real. Okay, and now, so what we will do is, we will show that a polarization kind of thing. This is what we'll do, and this will immediately finish the proof, because this has to be 0 for all. Assuming this hypothesis, the other direction is clear, so we will be doing this direction. So with this hypothesis, this will be 0, and hence this will be 0 for all v and w, and hence t would be 0. So to do this, nothing. We just compute the first term on the right hand side. So what is this? This is equal to that. But the first term is 0 by hypothesis. And the last term is also 0 by the same hypothesis. Now by self-adjointness, this is equal to right. So by self-adjointness, this is equal to that, because when you push t on the other side, it becomes the adjoint of t, but the adjoint of t is t. Okay. But this is equal to, by the property of inner products, And since we are working with real vector space, there is no need for conjugate. So this is twice of. Okay. And similarly, if you compute the second term, it will turn out to be minus 2 times this guy. So these two things will just cancel out. That's it. Right. So yeah, I mean, I don't know if there was any need for this 1/4. What was the need for this 1/4 then? So it's probably a half rather than a 1/4. So sorry, I said they will cancel out, but what I wanted to say was, sorry. No. Let's scratch that. What I want to say is, if you compute the last term, what you will get is this. This is equal to minus 2 TVW. That is what you will get. I mean, that you immediately get just by substituting minus W in place of W. Okay. And now if you subtract these two, what you will get is 4 times TVW. And when you do a 1/4, you get that. So I said they will cancel out. That was a very hurried misstatement. This is what is going on. Okay, so that finishes this proof and this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.